NVidia had their Computex 2024 keynote a few hours ago, so I delayed this video that I had planned to release earlier to add an information NVIDIA revealed that was relevant. While NVIDIA did not reveal the accelerator that I'm going to discuss today, they did reveal some information on Rubin, the successor to Blackwell, and Vera, a new CPU to succeed Grace. And that is where this accelerator will fit in. There's a lot to discuss, so I'll have to split this video into two parts. So let's dive in.
This video is sponsored by urcdkeys.com. If you pay full price for a Windows 11 key, you are wasting your money. Instead, you can get a Windows 11 OEM key from urcdkeys.com for just over $29, or even lower at $21.86 if you use my coupon code C25 at checkout. All URCD Keys product keys are on sale right now, so don't miss the Super Spring sale. Follow the link below to the Windows 11 page at urcdkeys.com. Click Purchase, enter your C25 discount code. You can pay with a credit card or PayPal, and then just add the Windows key to your Windows activation settings and you're done. The code is sent to you within minutes, by the way. You can also use my C25 code on other products, so if you need Office 2019, make sure to get it from urcdkeys.com for a much lower price than retail. Check the exclusive links in the video description to get your cheap OEM Windows or Office keys today from urcdkeys.com.
NVIDIA had a big patent dump this week, and as I looked through the drawings and descriptions, I remembered an accelerator that NVIDIA talked about back in 2022 at the VLSI Circuits conference. Before I explain what this accelerator does, we have to get a little bit technical for a couple of minutes, just so you understand the context for such a processor to make sense and why I believe NVIDIA is launching it next year. This accelerator is key to NVIDIA's strategy going forward. In fact, underlying Jensen's presentation at Computex were all the elements that will make this accelerator one of the most disruptive technologies that NVIDIA has ever launched. If we look back at the GPUs NVIDIA has launched in the last 12 years or so, from Kepler to Blackwell, which will launch later this year, one of the paradigm changes that were gradual but constant was a change in number representation native support. So in Kepler, operations were scalar at FP32, so that's 32-bit. And this was around 2012, which was when NVIDIA started porting models to their GPUs to see if the parallelism would benefit AI workloads. And obviously not only it did, but it has made NVIDIA one of the biggest companies in the world in just over a decade. Now Kepler was already out, and the next gen was already taped out, so it took a while until we started to see number representation changes, and FP16 was only natively supported in 2016 when the Pascal microarchitecture launched in the form of the P100 GPU. So NVIDIA reduced precision from 32-bit to 16-bit. Why does that matter? Well, in AI workloads, one of the low-hanging fruits for achieving greater performance was reducing precision. I won't get into how that works, but on an algorithm and API level, you can reduce the precision of the input and achieve the same results with less data, which means you don't get choked on bandwidth, but more importantly, you don't waste as much energy moving data around. Reducing precision works wonderfully in AI workloads, where you can prune the network of unnecessary data and focus only on the things that are likely to have the results you need. So after Pascal, NVIDIA launched in 2017 the V100 and introduced its now famous Tensor Core. A Tensor Core is just a fancy marketing name for an instruction, a complex instruction that is, called half matrix multiply and accumulate, or HMMA. Before, you had adds and multiplies, and now you have a complex instruction that does a bunch of stuff all at once. What that means is that you don't have to keep fetching stuff from memory. In other words, if the instruction is simple, but you have to keep fetching data from memory, you end up using a ton of energy in data movement, whereas the operation itself uses very little energy. I've explained this in past videos. So it makes sense from NVIDIA's perspective to have the instruction do more operations in one go and fetch the data less times. And that's what a Tensor Core does. It's an instruction that does a lot of things at once instead of just an add or a multiply. To give you an idea, back in the days of fused multiply-add operations, in the generations prior to Pascal, to do a fetch and decode, so that's data movement, that costs 30 picojoules, it was 40 times more costly to do that data movement than to actually do a multiply-add operation once you had the data, which cost a mere 1.5 picojoules. So that's a 2000% overhead because of moving that data around. It's only 1.5 picojoules to do the operation in logic, but it costs 30 picojoules to get the data from memory to do that operation. But with the introduction of this complex instruction, HMMA, or what NVIDIA's marketing calls the tensor core, the operation cost went up significantly because the logic is doing a lot more operations in one go, but the cost of moving the data was reduced massively. So now the same 30 picojoule fetch and decode cost 110 picojoule. But since the data didn't have to go back and forth for the rest of the operations to conclude, the overhead was only 22% instead of 2000%. It's a massive improvement in energy efficiency. So you have this balance of how complex do you make the instruction, which will result in the logic being active longer and using more energy per operation, and how much data do you move around. NVIDIA has so far figured that the cost of moving data around, in a 2.5D package at least, is much higher than the actual operations, and has therefore added more and more complex instructions to their GPUs over the years, always giving it a fancy marketing name. From Volta to Turing to Ampere and then to Ada, nothing much changed on the instruction level. What changed were the matrices' sizes. The next real big step was when another complex operation was introduced in the form of IMMA, which stands for Integer Matrix Multiply and Accumulate, when Hopper launched. So with Hopper, NVIDIA introduced 8-bit and 4-bit integer data types as inputs for those matrices. NVIDIA's marketing calls this the Transformer Engine. But like I said, that name is just marketing for another complex instruction. Now notice what happens to the energy cost of this new complex instruction in Hopper. The same 30 picojoule fetch and decode now only represents a 16% overhead, even though the operation itself is more costly to execute at 160 picojoules. And this is the very reason why dedicated accelerators from other companies haven't been able to catch up with NVIDIA, because of this balancing act between the operation cost and data movement. NVIDIA has gotten this right. This approach also means that NVIDIA can circumvent bandwidth limitations to some extent, like I said earlier, because you are doing less calls to memory. So this reduction in precision is achieved by natively supporting these different types of number representation, now down to int8 and int4. If we take a bird's eye view of where performance jumps have come from since Kepler up until Hopper, in workloads where precision can be reduced, number representation accounted for the greatest leap, at 32x when you take into account parasitics. Then the introduction of complex instructions resulted in a performance jump of around 12.5x. The process node is hard to say, but at least 3x, and sparsity another 2x. So that's why you hear Jensen on stage saying they achieved the 1000x performance uplift in AI in 8 years. The cumulative effect of all these changes are what led to that. And with Blackwell, well, it's 2 hoppers fused together, so you'll get another 2x. So you see that number representation has been the low-hanging fruit of achieving greater performance in this last decade. Of course, for all of this to work, you need the software to take advantage of it, and that's where NVIDIA's CUDA mode plays its part. But now that we're down to 4 bits, and if Blackwell is just 2 hoppers fused together pretty much, where is NVIDIA headed next? At Computex, a few hours before this video goes live, Jensen hammered on the fact that acceleration will be key, both in future PCs but also data centers. But key to what? Key to inference. Well, back to that Accelerator from 2022. As far as number representation, the next step will be support for log 8, which is log 4.3 along with a plus or minus symbol. I won't go into that here, but if you are on the Discord server, I'll be happy to explain there how this format works and why it's more performant than int4 in Blackwell when it comes out later this year. Anyway, more importantly, in addition to the work being done for training, NVIDIA came up with this dedicated accelerator back in 2022 that relies on 2 techniques to achieve greater performance in inference. These techniques are scaling and optimal clipping, to do large language models, for instance, without any loss of accuracy. As you can see in this graph from NVIDIA, with quantization you can map high-precision formats like Float32 to lower precision formats like int8. The reason you would do this is to achieve greater inference speed on resource-constrained devices. You know, devices like laptops. The particular technique that NVIDIA has shown in recent papers is VSQ, or vector-scaled quantization. So this is the first technique. The second one is clipping, like I said, which is another form of reducing precision without losing accuracy. So anyway, what does this technical jargon mean in practical terms? The accelerator that NVIDIA created does precisely these optimizations on the hardware level. An accelerator takes special data types and does special operations that are not natively supported on NVIDIA's GPUs, which means you can do in one cycle what would take tens or hundreds of cycles to do in Blackwell. An accelerator can also do massive parallelism but with locality, so it's massively performant compared to a GPU with a complex memory system. You also get optimized memory with high bandwidth and low energy for those specific data structures and operations. And the key ingredient is that you can do software and hardware co-design, so the algorithm can be specifically tailored for the hardware. As you can imagine, this is Jensen's wet dream. Yet another mode to force people into using nothing but NVIDIA, this time for inference. NVIDIA's GPUs are great for AI currently because they are programmable, they are flexible, they can adapt to new models and algorithms. But for micro operations that are to some degree agnostic to the developments in models, NVIDIA can build accelerators to improve performance, particularly in inference, which is where the majority of computation will move to in the next 5 years, while training will decelerate. So this is the layout of the test accelerator that NVIDIA taped out on a spare area of one of their network switches on 5nm and served as a prototype for what NVIDIA will be bringing to market, and which I believe could truly put Intel and AMD in a tough spot. So this accelerator does vector-scaled quantization, pruning, and clipping in order to support int4 operations. So it can do large language models without losing any accuracy at 5 times the speed of Blackwell, so almost 100 teraops per watt versus 20 teraops per watt on the B100 GPU that's coming out this year. Now note that this was on 5nm, so when Rubin comes out, so that will be the R100, either late next year or early 2026, presumably this accelerator will be on 3nm, so possibly 6 times as fast as Blackwell in inference workloads. It's also possible that NVIDIA will include it in the B200 next year instead. So when you use an AI service like a text prompt to do search, you enter your prompt, that text is then tokenized, so the whole text or some of the words or part of the word is split into smaller units called tokens, which are a unit of data that the AI model can understand. These tokens are converted into a numerical format, so FP32, int8, int16, int4, etc. So these are the number representations that GPUs work on to perform computation in the context of inference. So when you are doing queries locally on your computer or phone, you don't have the compute resources to do complex operations, so they have to be simplified and accelerated by fixed function units like this accelerator that NVIDIA has prototyped. Now you might be saying, but don't queries just get sent to the cloud and processed there? Why do I need them done locally? For one, there's sensitive security issues with personal data or company data that you don't want to be sent off premises. Secondly, you can think of service providers as AI clients themselves, and these accelerators will also be deployed there, sort of an intermediary level between yourself and the data center in order to speed things up massively. And thirdly, it's going to be much faster to do most of the computation locally and get an almost immediate response than sending all the tokens to a data center, having the processing done there, and then fetching the results. You want AI agents, ChatGPT and virtual assistants and whatnot, to respond immediately to your requests. So you need the operations to be accelerated locally. Without resources to do full precision, you need this accelerator to use the techniques I mentioned to reduce the number representation down to something like int4, so that even a phone or a laptop can perform operations that would normally require a bunch of powerful GPUs. Like I said, one of these accelerators locally on your PC is around 6 times faster at inference than a Blackwell GPU would be at doing the same operation. It's funny that in a way we're coming full circle. If you were around in the days of CPUs doing the 3D rendering in games and then saw the massive jump in performance that GPU accelerators brought to that rendering, you can think of GPUs now having the role of CPUs back then, and this new accelerator being as disruptive as GPUs were back then, except instead of accelerating 3D rendering in games, the workload mode is now inference. And you can bet that whoever gets inference right and makes it easy to implement will dominate both the edge server market but also client devices. Remember how over the past year I've been saying that NVIDIA will come to the PC market as a disruptor and leave the incumbents in a tough spot? Well, that's how important this accelerator is. It could define who will control the client PC market in the next 10 years. Intel and AMD are not prepared for this. Even if they have the hardware to compete, NVIDIA has the verticals. So that's the software that will make this accelerator a drop-in solution for a bunch of applications. To wrap part 1 up, how exactly is NVIDIA bringing this accelerator to market? There are 3 options. As a discrete PCIe card, similar to a discrete GPU that you slot into your system to accelerate graphics, but in this case it would accelerate inference. Secondly, as an integrated accelerator in an SoC. So this would be a heterogeneous chip similar to an APU, or similar to the Apple AMD chips, which feature a bunch of accelerators also. And finally, as part of a board or platform, similar to the Grace Blackwell superchip, but scaled down, possibly down to a laptop platform. Looking at the recently published patents on this accelerator, the first one titled Application Programming Interface to Transfer Information Between Accelerator Memory, we see the first embodiment of this accelerator, which is in a heterogeneous processor. In this 110-page long patent, basically NVIDIA is describing how different accelerators can access the same memory pool in a heterogeneous system. In essence, an API call from either CUDA or ROCm or one API is automatically split along the pipeline into the GPU and the accelerator, so that programmers don't have to code specifically for this accelerator. So in other words, NVIDIA patented a way for an API call to be automatically handled by the GPU, with the accelerator getting specific code generated for it, with both sharing the same memory. NVIDIA goes on to detail several possible variations of this and states that this can be both implemented in a single device, so that could be for example a laptop, or in a distributed computer system. The second relevant patent, published on the same date, is complementary and handles any API call errors. So it essentially handles where in memory any errors will be stored in such a system. The third and final associated patent describes how the processing occurs in such a system. Like I was saying, the API call is put into a stream that has all the instructions, and then some parts of the stream are allocated to the GPU, while other parts of the stream to the accelerator. Note that the patent states that the instructions in this stream that are meant to go into the accelerator can be distributed to multiple accelerators. So a possible implementation is having more than one of these accelerators to speed inference even more. We could see this being useful in edge servers, for instance, but possibly also in client devices. Now, obviously I'm simplifying all of the possible hardware implementations here out of the almost 400 pages of patents that I went through. But you can see that NVIDIA has kept the accelerator implementation wide enough, or rather open to interpretation, so as not to reveal too much, but still ensure they have all bases covered. Personally, I think it's unlikely that NVIDIA would release a PCIe type card for inference, even though that would be awesome. While not outside the realm of possibility, I think it's more likely that future generation of gaming GPUs will include this accelerator in some form, at least the high-end GPUs. So just like today, you can use CUDA to accelerate, say, video rendering in Adobe Premiere with your RTX 4070 or 4090, you could be able to use this inference accelerator in the future to speed up some of the verticals that we will look at in the second part of this video. I do hope NVIDIA releases a PCI type card for the consumer market. How awesome would that be? Another piece of hardware we can lust over, then spend an insulting amount of money on, and then never use it. PC Master Race style. So the other two implementations I think are the most likely approaches. So that's having a board-wide system similar to the Blackwell superchip, where NVIDIA could have an ARM CPU, either developed internally or licensed, a GPU chip, and then the inference accelerator, all sharing memory. And this could be used for laptops or workstations, for instance. And finally, the most traditional and I guess the most likely application would be an SoC in the vein of a large APU, with ARM cores, NVIDIA GPU cores, and this this inference accelerator to do the heavy lifting of AI inference locally. Depending on how large and power hungry this is, that could be a variant that would go into smaller devices and not just laptops, perhaps even a phone, or a new Shield tablet, or a virtual reality headset similar to the one Apple made and that everyone has already forgotten about, or a mini PC, especially with Dell hinting this week they will be selling AI workstations and AI thin clients or PCs next year with NVIDIA hardware included. So in part 2, we will look at why NVIDIA is wasting time with this when they are already banking massively on training hardware, selling millions of GPUs at massive margins, and also what applications we will see this used in. I don't think people realize how broad a scope such an accelerator will have, and the sorts of applications it can make viable, and that includes games. So subscribe to the channel right now so you don't miss part 2. And this coming week I'll also be covering the rest of Computex, so stay tuned for that. Consider joining my Patreon to support all this work of reading 400 pages worth of patents and going through NVIDIA obscure presentations in circuits conferences. And for just $2 a month, you will also get access to the Cortex Discord server. Thanks for watching, and until the next one.